Well, hello, my Theosophical Society buddies. This is Jeff Curtis coming to you again from the Sierra foothills. And interesting day up here. At the moment, I'm operating on battery power. And the power went off about 20 minutes ago. And the temperature is going up because it's 94 degrees outside. We'll see how long this computer battery lasts or how long I last. And we'll just take this as it comes. Um, I'm delighted to be able to speak to you again. I was informed today by Richard that this happens to be the 124th birthday of the San Francisco Theosophical Lodge, which that's quite a thing. It makes me feel pretty happy to be part of that. Theosophical Society, old, interesting, eclectic, wonderfully diverse, interesting organization, and the San Francisco Lodge even more so. I've been attracted to this for a number of reasons, but you don't really have to go past the so-called three avowed objects, and you've got me already. Okay, so object number one, forming a universal brotherhood of humanity without regard to sex, caste, creed, religion, color, any of that. Well, okay, two thumbs up. Second avowed object has to do with obtaining knowledge about science, amongst other things, religion, philosophy, all of it. Third avowed object, let's see, I got to take a minute and read this. What was that third avowed object? I already forgot it. Investigate the unexplained laws of nature and science and everything. So you can see why chemistry professor with spiritual inclinations and interests would be immediately pulled into this. So in acknowledgement of the second and third avowed objects, we're going to dive in here. And I'm going to do a little bit today trying to explain to you why scientists are just going crazy right now over the things we're learning and things we're unlearning from the data we're getting from the James Webb Space Telescope. That's what the JWST in my talk title is getting to. The James Webb Space Telescope was, I think its first images or its first official operation was on like Christmas Day of 2021. So it hasn't been with us that long. And then there was a long shakedown cruise. And then actual data collection started. And so those of you who have science interest in your feed from, say, YouTube or even just from Chrome, you've probably, even without looking for it, you've been bombarded with news and interesting stuff about what's going on in astronomy and especially cosmology, which is getting at the astronomy of stuff that's really far away. It's been coming at a rapid pace, and it's sort of an amazing pace, to the point where it's quite hard keeping up with it. I've been doing my best, but I gotta say, it has not been easy. So as I was, in part of my getting ready for this talk, I've been listening to YouTubes and scanning the literature, and came to me that I was a little bit ambitious, thinking I could cover all this in a single talk, and that's not going to happen. I think this is going to end up being another one of those series of talks kind of thing, partly because not only do I like giving you a high altitude perspective on current trends and news items, I think my history as an educator, I do like erecting a fundamental basis, a foundation for understanding. How do we know the things we think we know? So I'm going to spend a little while on that here tonight also, as well as just the news. one of the articles I was reading is from a very prestigious publication called Nature Astronomy. So the, the Nature Publishing Group has subdivisions of, there's Nature Chemistry, Nature Biology, and Nature Astronomy is one of the subdivisions. And so there was an article published on August 8th this year, 2025. The title was The First Billion Years, according to JWST, meaning this article was going to tell us about big changes and news, reasons we're going to have to reorientate our understanding based on JWST data, particularly focused on the first billion years of the history of the universe. Well, I'm thinking, hey, that's it. This is all I need. Well, started reading this article. One of the very interesting things that jumps out is the subcategory of what are called high redshift galaxies. And that leads me to bring up a notion, which is what's called the cosmological redshift, and you may have heard of this before. It's referring to how light gets stretched out and its apparent color changes if two objects are moving relative to each other. So suppose I'm having light being emitted here and I've got a detector built into this pin. Well, if they are at rest relative to each other, this pin is going to read a certain wavelength of light. On the other hand, if this pin is moving, or if the emitting body is moving, it's going to stretch that emitted periodic wave. And what that ends up doing is causing something we call a redshift. The acoustic analogy of this that you've heard a million times is the Doppler effect with respect to sounds. And when you hear a car approaching from one direction, the sound from its horn will be higher pitched, and once it passes you, it goes lower. So you get a kind of a percept. That's because of the waves bunching up as they move towards you and then stretching out as they move away from you. That happens to light as well. And astronomy, cosmology, it's all about light. It's all about gathering as much light as you can over as broad of a wavelength region as you can, and then analyzing it as deeply and intelligently as you can. So one of the critical parameters that comes out of that is redshift of light. Well, I am once again going back to my old-fashioned way of presenting information. This is actually a slide from an old talk of about 2 years ago where I was talking about the basis of spectroscopy. And spectroscopy is based on analyzing light, which is correlated to allowed quantum gaps between, say, electronic states or vibrational states or even rotational states of atoms and molecules. They can be in outer space. And in fact, we have a whole subcategory of astronomy based on molecular rotations, and which are quantum gaps or spacings between rotational levels of molecules or molecular ions in space. The vibrational spacings tend to fall in the infrared region. Gaps between electronic states, meaning electron orbitals around nuclei, those tend to fall in the UV and the visible range. But that's only when the emitter and the detector are nearby and stationary, rather. If they're receding from each other, you get a redshift, and we measure it with a parameter called Z, and that's why I'm bringing this up. So the cosmological, well, any kind of redshift, we're going to be talking about cosmological redshifts. So Z is just equal to the wavelength of light that you observe or measure minus the wavelength at which it was emitted from the source divided by the emission. So obviously, the higher the z value, it means more the higher the velocity of the recession between emitter and receiver. So that's what we're going to be focusing on. Well, a redshift of 14 is huge. Until just recently, we couldn't even measure those. It's because of the James Webb Space Telescope that we can even do that. Now, this instrument was designed for that. The James Webb Space Telescope is different. It's a huge upgrade, and it's very different from the Hubble. The Hubble Space Telescope, which we've all seen beautiful pictures that come from it, that was put up there in 1994, and it's still working, by the way. It's still doing research. We put telescopes in space because it gets them above the atmosphere and the turbulence. And it's particularly important for infrared and near-infrared astronomy. The Hubble, its wavelength range is not it's not a reason it has to be in space, because the Hubble wavelength range goes from about 200 to 1,000 nanometers. So that means UV into the tip top of the near infrared at 1,000 nanometers. That's a good chunk of the visible spectrum, most of which gets through the Earth's atmosphere just fine. Not the UV part, but the visible and the near infrared gets through Earth's atmosphere fine, but it's scrambled by the motion of the atmosphere. Well, the James Webb Space Telescope has a much larger mirror. It's about 2.7 times bigger mirror. That means it's collecting more light. The Hubble is 86 inches diameter. The James West is 234 inches diameter. That's a ratio of about 2.7 in the diameters of the two telescopes. But very importantly, and this is why astronomers, even amateurs like me, who go out with little amateur level telescopes, we always want bigger and bigger ones. Well, the light gathering capacity goes with the square of the diameter. Not actually square of the radius, but it doesn't matter. So if you go from 86 inches to 234 inches, that's a factor of about 2.7. The light gathering goes as the square of that, which turns out to be about 7.3. So the new telescope, the James West, is collecting more than 7 times as much light in a given unit of time than the Hubble. That's a big deal. Also, the James West, if you've seen pictures of it, you may have noticed that the mirror is kind of interesting, octagonal-looking, segmented thing. What a miracle. They could send that up in segments, and they would unfold, and you get this beautiful mirror that has got that segmented structure, and it's perfect geometrically aligned so that we get good images. Well, that factor of 7.34 actually in area, that's huge. Also, the difference in color. That's because that mirror, the James Webb mirror, is actually a fine layer of gold, which has been deposited on, I think it's a beryllium base mirror material, very complicated materials science involved. That has its optimum reflectivity in the near-infrared region. So the whole span of it goes from about 600 nanometers, which is optically in the red light, all the way out to 5,000 nanometers, which is really long wavelength, very much in the infrared. It was designed that way because we knew we wanted to probe really far out there into space at cosmological distances. The Hubble, you've seen pictures of that one maybe. It's just a single round optic in a traditional sense, 86 inches across, and it looks silvery. It's actually a thin aluminum coating on a glass mirror, which is very traditional. That's how just lots of standard reflecting telescopes you can buy online, or used to be able to buy at department stores when department stores sold cool stuff. That's very common kind of technology. Well, so what I'm getting at is that we knew we were going for the infrared. How did we know that? Well, because we're trying to probe farther and farther back in time. That means there's more and more space between the emitting stars, or whatever we're seeing, and us, because we know that space is expanding. The more space there is between two things, the faster they're receding from each other. This is one of the major central tenets of modern cosmology. So this thing was designed to run out there into the infrared and allow us to see very far away, deep, redshifted objects that would be invisible otherwise. And of course, all the detectors are newer, better, and they're tuned into that wavelength region, which is very different than where the Hubble was tuned. So those are some of the kind of practical differences. In terms of resolution, they're not that different. Resolution being how fine of a detail can you see in something. Well, that goes as 1 over the diameter. So you might think, well, the resolution of the James Webb Space Telescope, since it's approximately 3 times bigger diameter, it should have 3 times as good of a resolution. That doesn't quite happen, because resolution goes down with the wavelength of the light you're looking at. And so in general, the resolution from the James Webb is somewhat better than Hubble, but not spectacularly. What's spectacular is the wavelength range and the amount of light being gathered, and the sensitivity of the detectors is completely different. Well, back to this article from Nature Astronomy. It's all about how amazing it is that we're seeing Z=14 redshifts, and turns out if you do the math, which is not that complicated, that if you see something at a Z value of 14, that means you're seeing things that are quite young in the history of the universe. They're only about 275 million years old if they're sitting at that redshift of a value. This all comes from computations based on the theory of general relativity and the nature of how much space is intervening between two objects. That means we know how fast they're receding from each other. Okay, Z14 is a big deal. The fact that we're seeing galaxies, that means a distributed object with structure in it that has had time to form stars and coalesce, get a structure like what we're familiar with in galaxies. That is complete news to our previously existing model of how the universe works and how galaxies form. It was, or rather is, a huge puzzle to modern cosmology. We didn't think galaxies could form that fast, much less in big numbers, and have well-developed stars. Furthermore, it turns out with more recent observations and reading some other papers, the galaxies like this one I'm talking about at Z14 is chemically enriched, meaning that we can see evidence of there being oxygen and nitrogen atoms at some level of abundance in those stars from that ancient object. That's very surprising, because the only way you get oxygen, and especially nitrogen, formed and present and measurable in stars is if those stars have coalesced from gas expelled by previous generations of stars which had to explode. So we're seeing galaxies at Z=14 composed of stars that are already second generation stars. That's very far outside how we'd been thinking up until now. There's a model of cosmology. You've heard me refer to the standard model of quantum mechanics. That I've gone on at length about that in various talks in the past, and that's the foundations of something we call quantum field theory, which grew out of quantum mechanics. There's also a standard model of cosmology. It's called the lambda cold dark matter model, and it's a set of assumptions and a mathematical structure that purports to enable explaining the evolution of the universe from the Big Bang and then the evolution of stars and galaxies and all the stuff. And it turns out that most of the stuff is actually dark matter. Only about 5% of this stuff is baryonic matter, which is the kind we're made of and we can see and detect and interact with by light. So already we're seeing a need to rewrite the textbooks, rethink everything. How can there be whole galaxies made of at least some amount of second generation stars by 275 million years after the Big Bang? There's something we're missing. Well, okay, great. That article came out on August 8th. Obviously, it had been submitted quite some while before that. So paying attention, as I've been over the last week or so, it's now a whole new thing. It's a whole new situation. Over the last 5 or 6 days, there's been an announcement of at least 6 objects identified at a Z shift of 17. And then there's 3 objects that have now been identified at a Z of 25, which means we're getting down to like 1% the age of the universe. We're seeing stuff with this telescope. That's just extraordinary. We're not quite sure what that stuff is. That's still sort of up for grabs. We're not talking, this is difficult to detect. Why are all these revelations coming right now? Well, it's because we've had long enough to stare at a single patch of sky and build up the image. You don't get pictures like this in a snapshot. This takes long integration times. So we're coming up on 5 years-ish operation time of this telescope. So now we've had time to stare at specified patches of sky for longer and longer intervals. And it by the way, it doesn't have to do it all in one shot. It can do that for a while and then go do all other kinds of astronomy and look at planets and nearby stuff, nebulae, and then come back and look at the same place. As long as they can line it up and be on the same part of the sky, they can add those images electronically and eke out what we call optimum signal to noise. Because in any single exposure, you're going to have some amount of signal, some amount of noise. Astrophotographers are all about length of exposure because over time, the signal adds up, whereas the noise cancels out. The noise is random. So the noise in your detector and your electronics over time self-cancels, whereas the signal is always there at the same frequency and in the same position, and that adds up over time. So I think that's why we're just now getting all this big weird news from JWST, is that we're finally beginning to bottom out on the exposure times. Although we're not really bottoming out. We're just getting to a whole new level of the mystery, and we're getting one huge slap in the face about how little we really knew. And that's what's fun about this. Okay, so what do we take from this? Well, these new objects being observed at Z of 17 and a Z of 25, they don't quite appear to be galaxies. People are scratching their heads and guessing. One guess is that, for example, the objects at Z17 might be what are called black hole stars. This would be the case where some giant primordial cloud of gas has condensed enough that a star is formed and started burning, but the whole thing keeps collapsing. And theoretically, at least, some of the models suggest that it's possible under circumstances of a sufficiently large cloud collapsing slow enough that you can have a black hole form on the interior of a star but not disrupt it. So not get the standard or typical supernova explosion that we see at the end of the lifetimes of normal stars, but rather we have a big cloud of gas with a black hole in the middle of it burning. That's one possibility. Another possibility, particularly thought of now in regards to the Z equals 25, really very ancient objects, is that those might be what are called primordial black holes. So a giant cloud of gas post-Big Bang collapses in on itself and boom, just goes straight to a black hole. Again, without the big supernova explosion. Or maybe with, we don't know. It's really all guesswork at this point, which is quite exciting. I mean, scientists love this. It's something you would never guess from the typical undergraduate education in any given discipline of science is how much the scientists would love for their textbooks to be massively wrong. If it comes out that this textbook you've been teaching from for the last 23 years and all dog-eared and the pages are starting to fade and getting ready to fall apart, we love it when that stuff turns out to be wrong, because then it means there's a whole new round of discovery getting ready to happen. And it's exciting for everyone. There's always a certain contingent of kind of anti-expert people in the public who, yeah, well, you scientists, you don't know jack. Actually, we love that. When there's a revolution in any particular science, it's liberating and joyful for the professional scientists who are in there doing the work. It's maybe annoying for some professors here and there who would rather be able to keep using their old notes, but that's not very many of them, and it's not the ones who matter the most. This is a great moment that we're in right now, because we are learning a lot and we're learning it fast. And it's going to take a long time for our theoretical models to catch up with the flood of data coming in right now. It's particularly shocking to me that there would be chemically enriched galaxies, meaning second generation stars in a galaxy that's only 275 million years old. And of course, I keep saying that like it's something I know. Where does that come from? Well, that idea that the universe is 13.8 billion years old comes from data that's been around for a long time. The so-called Hubble expansion, Hubble in that case referring to the astronomer who discovered it, the fact that the farther away a galaxy is, the faster it seems to be receding. In other words, the bigger its Z value, the more redshifted its light. So Edwin Hubble was the first astronomer in about 1929 who began figuring this out and putting it together. The farther away galaxies look redder. Why is that? And they didn't know at the time. In fact, they had just figured out that those smudges out there were other galaxies. That work was mostly based on the 100-inch telescope. The one at, I think it's the Lick Observatory. It was the big revolutionary telescope of the day. That 100-inch telescope was the first one to figure out that if you look at the Andromeda galaxy, which is a big smudgy thing, and you can see it with naked eye, you can see it as a large smudge on the sky in the constellation Andromeda, which is there right next to Pegasus. If you're someplace dark and clear, like actually where I live, you can see that thing by naked eye. It was called a nebula, meaning cloud, for millennia. Only in about somewhere in the 20s, Edwin Hubble, working with that telescope, realized those are stars in there. That thing's not a cloud of gas or some smudgy piece of goo. That's a huge association of stars. Oh, that must be another Milky Way. We're looking at something like where we live, but it's way up there. So Andromeda is a very large galaxy, and it's very close. It's part of what we call the local group. So Edwin Hubble had this realization, oh, stars, Andromeda, those other things. Let's look at, there's this huge catalog of nebulae, clouds in the sky, compiled first and most famously by a French astronomer named Messier, the so-called Messier catalog. So Hubble was looking at the Messier clouds, patches, originally cataloged by Messier so that people wouldn't mistake them for comets. Messier was a comet hunter and interested in comets. Well, these annoying patches, smudges on the sky could confuse comet hunters into thinking they were something interesting. Messier cataloged where they were, wrote their positions down so that people would know to next keep looking if they, like he, were interested in finding comets. Well, turns out when you look at those Messier objects, some of them are in fact clouds of just gas and dust here in our own galaxy, but others are different galaxies at great distances away from us. Some of them have a spiral structure, some of them don't. There's different kinds of galaxies. I'll go into that in a later talk as we go on in this series. But the main point being that Hubble very quickly, was absorbing all this data, new ideas, and he was the one who went out and realized, oh, farther away, more redshifted. Okay, I want to back up at that point and question some of these things I'm saying. I think partly my career as an educator in sciences, chemistry in my case, we're always interested in how we know things. How do you know that? So how did Edwin Hubble know that those galaxies were farther away? Well, there's some immediate hints just in how big and bright they look, right? You might think, well, smaller and fainter is probably farther away. That works pretty well, but it doesn't work well enough. There has to be a better way, and there is. There's a giant construct now that scientists use. It's called the cosmological distance ladder. And it's, how do you go about figuring out the distance away something is using nothing except the light you're gathering with a telescope from the ground? Well, it's a hard question. And many astronomers have devoted their lives to just getting a little farther into that and beginning to either make the distances more accurate or pick off a new category of distances. And it's quite a long story. But let's start close to home, and let's think for a few minutes here about distances, and then I'll wrap up because I have a battery issue, and it's getting hot in here. You might think of a couple beginning distance scales that we could discuss. So first off, let's think about how do we measure distances to stuff that's close here in our solar system. One to pick and think about particularly might be the distance from the Earth to the Sun. How do we know what that is? Well, almost everybody learns in elementary school that that's called 1 astronomical unit, and it's 93 million miles. Okay, how do we know that? Well, first people to really think hard about it and actually start coming up with numbers were, of course, the ancient Greeks. And they did okay. I mean, considering what they had on hand, which was like no instruments really, the first person to come up with a plausible size, order of magnitude number for that distance was Aristarchus. And Aristarchus worked with pieces of knowledge that he already had available to him, because in about 200 BC, Aristophanes and Hipparchus came up with reasonable estimates, both of the circumference of the Earth and the distance from the Earth to the Moon. So Aristarchus used those numbers and an observation of parallax and just geometrical arguments. He came up with an estimate back in about 140 BC that the Earth-Sun distance was about 5 million miles. It's actually not too bad. I mean, 5 million, 93 million, that's, at least they're not different by an astronomical amount. They're in similar league with each other. And that's kind of where it stood for a long time. The first modern approach to the Earth to Sun distance started in about 1672 with the famous astronomer Cassini, the guy who the satellite or the spacecraft, the Cassini probe was named after. He used Kepler's laws, and he improved Aristarchus' measurement by a couple of factors, but he wasn't able to get too far. He based his work on skillful use of Kepler's laws and the parallax of Mars, and he was able to work out an Earth to Sun distance that was better than Aristarchus, but wow, 1800 years later, okay. Along came Edmund Halley, the guy famous for discovering Halley's Comet, and he was the first of a series of astronomers to realize that we could use data from the transit of Venus. So every once in a while, Venus will crawl across the face of the sun as viewed from Earth. You might think that all the sun and the planets are all on a perfect plane, and so that there would frequently be situations where, as viewed from Earth, we would see the disk of the planet Venus go across the face of the sun. It's actually kind of a rare event. My wife and I had the joy of watching one of those happen some years ago. It was actually before we were living up here in the mountains full time. But it was great. We set up a telescope and projected an image and invited people we knew and had this big Venus transit party. It was quite a trip. And you could just see the planet Venus at a certain point in time hits the edge of the sun. We're projecting the image, of course, not looking at it straight by eye. And you see this black dot slowly crawl across the face of the sun, and that's the planet Venus. Well, Halley realized way back then that if you had people at different points on the Earth time exactly when Venus hit the edge of the sun and exactly when it left, you could use those time variations from place to place on planet Earth to compute the Earth to Sun distance at the next level of precision. And they did. So there was a series of these transits got observed in an organized fashion by people over time, in some cases by people who sailed on ships to certain places in the ocean to just be there and watch the transit and be the person to time it from that particular latitude and longitude. So it was a global organized effort of scientists. Finally all came together in about 1761 with the work of Jerome Lalande, French astronomer, but obviously working in conjunction with other people and previous measurements. And they were able to nail it to within 3% using that method, which is pretty impressive. And kind of a nice testament to people working together on a truly global issue across global boundaries. All right, so almost modern scale accuracy, 1761, cool. Modern times, we can nail it to within a few meters, and the way we do it in modern day is using radar and spacecraft. So with modern electronics and data collecting objects off of the Earth, this problem becomes much easier to solve. And so now we measure the Earth-Sun distance. We know it to Well, I'm not exactly sure if it's meters or centimeters anyway. It's hard to say because the sun doesn't really have a surface. It's everything's much more wobbly than that. It has a center of mass, and so we'll use that. What we do know is that now our resolution is sufficient that we can measure the rate at which the Earth and the Sun are getting farther apart. So Earth is slowly receding from the Sun, very slowly. A few reasons for that has to do with the fact that the sun is burning its nuclear fuel, so there's an ongoing mass to energy conversion process happening on the sun. And then there's also energy being lost by tidal forces between the Earth and the sun. And so just like the moon is receding from the Earth because of the action of tides burning off energy, turning potential energy into kinetic energy, that is happening between the Earth and the sun. And so someday the Earth will be far away from the sun. It's not happening fast enough to be worried about, but we can measure it now. We know what that rate is. I didn't write it down, but it's a known quantity. Okay, so cool. We have now a distance ladder. We know how far away the sun and the moon and the planets are using a web of modern technological measurements. But what about stars? So the first distance we might begin to call a cosmological distance would be, how far is it from us to the stars? Well, people started thinking about this a long time ago. And it actually became a relevant point of conversation back even in the days of Copernicus. So you'll remember that Copernicus was the first one to realize the so-called heliocentric model. He figured out that the Earth and the planets revolve around the sun, not vice versa, them revolving around us. Well, people at the time even pointed out as an argument against Copernicus, and they said, well, suppose the stars are miniature versions of the sun. That was not universally accepted by any means, but more forward-thinking people at least considered it. If that was true, if the Earth was really revolving around the sun, wouldn't we see the stars shift around? The answer is actually yes, but they were shifting by such small amounts that it couldn't be measured using the instruments of the time. So it turned out to be a clever but wrong argument against the Copernican model of the universe, or the so-called Copernican cosmology. Now, what am I getting at there? So you think about the Earth's orbit. We know it's 93 million miles radius. Okay, so that's a pretty big diameter, 2 times that. That's a lot of millions there. If you were to look at the sky very carefully and make measurements of stuff 6 months apart, the Earth going around in a circle, actually it's an ellipse, but pretty close to a circle. 93 million times 2. That's a big baseline of a distance. If you're looking at stars, wouldn't the close by ones move? Well, that was our argument to Copernicus. Turns out they do move, but not by very much. So I'm going to do a little demo here. This is a protractor borrowed from my wife. This is a physical therapist's joint range measuring protractor that has a hinge in the middle and a nice degree scale. If I move this thing, okay, got it lined up there at the 0 point. If I move this by 1 degree, it looks like that. So the difference is to go from there to there. That's 1 degree. You can barely see it. If you just look at the edge of this, There's a degree. Okay. 0. Let's go to 1 degree. You can just sort of barely perceive the extent to which that's not straight. If I hold that thing up next to my pad of paper, you can see, oh yeah, there's a gap there. It's not a straight line. So a degree, we call it a degree of arc, and we know that there's 360 degrees in a whole circle, right? Well, a degree of arc is not much. Degrees are subdivided into minutes, of which there are 60 in a degree, and those are subdivided into seconds, or arc seconds, of which there are 60 in a minute. Turns out that if we look at the very closest star, which is, well, let's call it Alpha Centauri. There's actually Proxima Centauri. Its companion is a little bit closer to us, but not. Let's talk about Alpha Centauri. The first measurement of this that worked was conducted in 1832 by a South African astronomer named Henderson. He did this measurement looking at the position of Alpha Centauri 6 months apart and measuring where it was relative to the other stars in back of it. So imagine, you've all seen a parallax demo. You kind of know what it is just intuitively. If you say close your left eye and line your finger up with something, a door jamb or an object on the wall, and you then close your right eye and look through your left eye, you'll see the image of your finger shift to the right. So looking at my finger through my right eye, swap over to the left eye, the apparent position of my finger shifts to the right. That's called parallax. So parallax is what happens to a near field object relative to distant objects when you change your point of position. And I have great figures for this. I was hoping to show you, but it just didn't work out for reasons of technical difficulties and a power outage. But maybe next time I'll be in modern times and I can show you nice figures. The amount of shift of Alpha Centauri that came from a 6 months baseline, therefore twice the Earth-Sun distance, shift in our position was about 0.77 arc seconds. So an arc second, if you go back to this, an arc second is 1 over 3,600 of a degree, right? That all works out to be about 1 over, if you do the whole thing, there's about 1.2 million arc seconds in a full circle. That's a pretty small amount. So Henderson first measured this 0.77 arc second variation in the position of Alpha Centaurus relative to the background stars, some of which were far enough away that you could really effectively assume them to be infinitely far away for purposes of doing the math. He was able to show by that the distance from Earth to that star had to be 4.24 light years. And he was right. It's been, I'm not sure that's exactly the number he got. I think that's the modern number. But he was very close to getting the modern number back when he did that. Arc seconds, by the way, just point of information, is kind of fun. Where do we get this? We're dividing a circle up to 360 degrees and then divide them by 60 minutes in a degree and then 60 seconds in a minute. It comes from the ancient Sumerians. they had a base 60 mathematics that they worked in, which is rather remarkable, and stands as one of those great mysteries of history. And uh, you know, a lot of people would immediately start talking about ancient aliens, and I don't know. I hope that's true, but uh, it's interesting no matter what. We're still using it today. So thank you, Ancient Sumer, for helping us out there. About this time, so there were verifications by different workers who came along afterwards. Struve, Bessel, a famous astronomer and mathematician, I think, of the day, came along a few years after Henderson. And in the late 1830s is when this science of parallax measuring kind of matured and became accepted and utilized on multiple stars. And we began to realize, oh yeah, there are some stars that are close, there are some that are far, and we can now begin to expand our quantitative handle on the local universe by using this method. And it can get us out. How far can you measure using this depends on how good your measuring apparatus happens to be. So by using the Hubble Space Telescope, which is a very precise measuring thing, and it truly is measuring star positions relative to infinity, because we can use distant galaxies as the reference point. We're able to push this method out to like 10,000 light years now. It was only applicable out to 10 or so light years back in the day. There's a famous unit of measure that you've probably heard about. So it was about this time in the 1830s, people realized, oh, we can come upon a standardized unit of astronomical distance if we just define anything out there in the far universe that results in a parallax of 1 degree. We're going to call that distance a parsec. It turns out to be 3.3 light years, and you've heard it mentioned before. Sometimes you'll hear it incorrectly used. The parsec, you'll hear it sometimes used as a unit of time in more sloppy science fiction stories. You'll hear it correctly used as a measure of distance, 3.3 light years, in the more careful and sophisticated science fiction movies. And it's part of the language now. That's the language of parallax measurements in astronomy, if you ever hear the word parsec used in connection with cosmological distances. And so, with that, I'll close. And I thank you all for hanging in with me. I'm realizing now I went overtime. I hope it's worth it. My battery lasted, so take care. I'll see you all next time. Bye.